Welcome to Sundar's lecture. This is lecture number 76, and in this lecture we are going to just continue the last problem. See what we have taken in the previous class. This is the numerical problem with RLC circuit, and we are exciting the circuit with the DC input, right? So we have already seen this one. We have three cases. One is overdamped, and the second one will be critically damped, and the third one will be underdamped, right? So we have seen both overdamped and critically damped in the previous class. See, this is the overdamped condition, and then we have gone for critically damped condition, and we have just solved the problem and we have compared both overdamped and critically damped, right? So what we have concluded in the previous class, so critically damped condition, at a critically damped condition, the voltage stored in the capacitor will take less time to reach 10 volt. That is the obvious point, you have to note it down when compared to the overdamped condition. See, at 1.5 seconds, here the voltage stored in the capacitor is 8.57, but at 1.5 seconds, the voltage stored in the capacitor is 9.91 volt at a critically damped condition. Right, now we will go for underdamped condition. Right, what we are going to do here, let R which is equal to 2.5 ohms now, 2.5 ohms, and we know both L and C, right? L is equal to 1 Henry and C is equal to 0.05 farad. That we have already taken. I have also already told you that I am not going to change L and C, right? So now what we are going to do, we need to find alpha. What is alpha? Alpha which is equal to R by 2L, and if you substitute this one, you will get 2.5 divided by 2 into 1, and obviously you will get it is 1.25, right? And we know that omega naught which is equal to 4.47, right? We have already seen this one. Maybe you take 1 over root LC, obviously you will get the value of 4.47. And what is the condition? We can easily understand, right? This is alpha is alpha is less than omega naught. And I have told you already, what is the nature of LC circuit? LC, if you are considering only LC, then we have seen, please refer my previous lecture to see what happens when I excite DC voltage, when I excite the series or LC circuit with the DC voltage. Obviously, you are going to, not DC voltage, maybe only LC circuit with energy stored, any one of the component. Maybe we have assumed that the capacitor has 10 volt, and then we have seen that it is oscillating. Voltage and current in the circuit is getting oscillated, maybe sine wave or cos wave, you will get any one of the waveform, right? So we have seen those kind of things already. Now this is the condition, alpha is less than omega naught, and we have seen that if alpha is less than omega naught, then what is the condition? What is the nature of the roots? See, alpha is less than omega naught, then obviously your roots will be complex conjugate. That we have already seen. And now we try to find what is the value of S1 and S2. And what is S1? S1 will be is equal to minus alpha plus square root of alpha square minus omega naught square, right? This is the formula. And if you substitute here, you will get minus 1.25, and then it will be plus square root of 1.25 square minus 4.47 square. Now this is the value. And if you further simplify this, then obviously you will get S1 which is equal to minus 1.25 will be there, and then this value will be plus 4.30 J. You will get like this. Maybe if you simplify this, you have to keep your calculator in the complex mode, so that only you will get this value, otherwise you will get a math error. Right now, if you simplify this, you will get this value. Then obviously, similarly, if you are going for S2, what is the formula? Maybe minus this value, maybe I will write it down anyhow, so that you will understand. What is the formula for S2? S2 is also very simple, that is minus alpha minus square root of alpha square minus omega naught. So it's same thing, you will get it in the negative value, right? So what you will get, then S2 will be is equal to minus 1.25 minus 4 point this value minus 1.25 minus 4.30 j. That's all, right? Now this is the value of S1 and this is the value of S2, right? Now what we need to do, see both values are a different one, right? This is a different value and this is a different value. What is the solution for the differential equation? What is the solution for differential equation? Maybe if you are going for V of t, then it will be a e power s1t plus b e power s2t and then it will be plus 10. Please refer my previous lecture how to get the solution for a differential equation. You will get a second order differential equation and you simplify the second order differential equation, you will get an expression like this. Now you need to find what is, maybe we know what is s1 and s2, right? We try to write down the expression. So v of t can be written as a e power, what is s1? It is nothing but minus 1.25 plus 4.30 j into t and then in between there is a plus, so b e power, this value is minus 1.25 and minus 4.30 j, the whole this whole term will be multiplied by t, then it will be plus 10. Now this is the expression and we have assumed this one, right? V of 0 is 0, I of 0 is 0. So if you simplify this one, what you will get? So if I am going for V of 0, so V of 0 value will be 0, which is equal to, if t is equal to 0, then e power 0 value will be 1, so it will be a, and e power again it will be 1, this value e power 0 will be 1, so it will be plus b plus 10, and that's all. That's all. If you keep this one, so a plus b, you keep it one side, that should be, and that value should be is equal to minus 10. Make it as expression number 1. We have got one expression, right? And what we need to do, we need to find what is, we need to substitute I of 0 is equal to 0. Then we need to go for the I of t expression, right? So how will you get the I of t expression? It is also very simple. I of t, which is equal to, it is 0.05 c dv by dt, right? So d by dt of a e power minus 1.25 plus 4.30 j into t. I need to write everything, right? B e power minus 1.25 plus 4.30 j into t, and then it will be plus 10, right? Right, this is the expression, and if you simplify this expression, what you will get, you have to get this into the front side, because maybe I will write it down. I of t will be is equal to, now it is 0.05, we know this one, and we have to bring it to the maybe this is in power, and we have what is the differentiation of e power at, it will be a into e power at. So what you will get, then obviously you will get it to be minus 1.25 plus maybe you will get like this 4.30 into a e power, and then this value, maybe see this whole term, maybe I will take it as small a, and this whole term I will take it as small b, so that it will be very easy, right? Or otherwise I need to write again and again to this one. So this value, it is at, maybe I will write like this and then we will replace it. Then this value will be plus e power, and then what you will get, sorry, you will get minus 1.25 minus 4.30, this is minus, 4.30 into b e power bt, right? That is the only term, right? Because plus 10 value you will get 0, right? So now if you multiply this one inside this 0.05, you will get an expression. I will write it down, that expression now. And you see this is the value of it, this is the value of it, and we know that what is the value of I of 0? I of 0 will be 0, right? So if you substitute, maybe if you substitute I of 0 in this expression, and that has to be 0, and this value will be 1, right? This value will be 1 and this value will be also 1, right? Here it is e power, so this both values gets to 1, right? So only you will get this value. So this will be minus 0.0625, I will write firstly. This value will be 0.125j into A plus 1 minus 1.25, and then it will be minus 4.30j into B. This value will be equal to 0. And if I further go for this one, what I will get, if I bring this term to the other side, so if I take minus outside commonly, this value will be minus into the whole value, it will be plus. So what I will get, then obviously I will get minus 0.0625 plus 0.125j into A will be is equal to 1.25 plus 4.30j, this is 4.30j, the whole term into B. And I can easily find what is A now, right? Yeah, maybe I will get to the next page. So you see, I can just bring this term to the denominator. So what I will get? So A can be written as that is equal to 0.0625 plus 0.125j, and then whole divided by I will get minus 0.0625 plus not yes, it will be plus 0.125j, and this term will be B, right? So if I further simplify this, and I will get A in terms of B, I will get it to be 0.6 minus 0.8j into B, right? Now this is the expression number 2. And if I substitute 2 in 1, I will get a final answer. I will just write it down the final answer directly. You please go through this one, or if you substitute yourself to get the values, right? So I will get B is equal to minus 5 minus 2.5j. You just try to substitute this one, make it as expression number 3, and if you substitute 3 in maybe into, and what you will get A value, and you will get A to be minus 5 plus 2.5j. Make it as expression number 4. Anyhow, I don't need this one. So now this is the final expression, right? Now this is the final. You got what is the value of A and what is the value of B. So what you can write it down. Maybe you can go for V of T expression. Right now this expression can be, you can substitute A and B in this expression. So what you will get, maybe I will write it down. So V of T now can be written as minus 5 plus 2.5j e power minus 1.25 plus 4.3j into T, and then there is a plus. This value will be minus 5 minus 2.5j e power, if you go for this one, this will be minus 1.25 plus, not plus, it will be minus 4.3j into T, this will be plus 10, right? Now this is the value. And you try to simplify this. You try to simplify and get an expression like this. I am not going to solve everything. You try to do yourself. This value will be now 1.25 e power, sorry, you will get e power minus 1.25 t multiplication of minus 5 into you will get e power 4.3 jt, and then plus e power minus 4.3 jt, this is one term, and you will get plus 2.5 multiplication of j e power 4.3 jt, and then you will get minus j e power minus 4.3 jt. That's all. You will get an expression like this, and then this plus 10. This plus 10 will be always there. So and then this plus 10. See, we know both formulas, right? What is the two formulas we've already seen? E power j theta plus e power minus j theta can be written as what? 2 cos theta. And also we can write j e power j e power j theta minus j e power minus j theta can be written as minus 2 sine theta. This is the expression we have already seen. See, both are like that, right? This is the first one and this is the second one. And if you further simplify this, we can easily write what is the v of t value. What is v of t? So v of t will be is equal to minus 1.25, and you will get an expression like minus 10 cos of 4.3 into t, and then you will get minus 5 into sine of 4.3 into t, and then this whole expression will be plus 10. That's all. Now you see, this is the final expression of an voltage stored in the capacitor, right? You see, we can easily get the point now. If you put this is t, this is actually t. If you put t is equal to 0, what you will get? What you will get? Then obviously sine of 0 will be 0, right? Sine of 0 will be 0. This whole term becomes 0. Everything will be 0, right? You will get a minus 10 here. This value becomes 1. What is the value of minus cos? This is, if you put e power 0, the value will be 1. This value will be 1. No problem with that. Then cos of 0 will be what? It will be 1. So it will be minus 10. This value becomes 0. Then minus 10 plus 10 becomes 0. Because we have taken an initial condition to be 0, right? So it will start from 0. Maybe we will see that. Maybe I will try to put the value of t is equal to 0, 1, 1.5, 2, 2.5. What we are getting? Let us see what is the values of voltage we are getting for every seconds, or maybe half a second, 0.5, 0.7, 7.5. Everything we will see after. And now we try to get what is the value of I of t, right? We will do that. So I of t can be written as what? We have seen this one, right? See here, maybe you see here we have just written the values, right? This is the value of I of t. We have taken it out, and we try to write down this value in the last page, and you see you will get an expression like this. See, I have just written this one with A. And what is A here? This A, this small a and small b have just substituted, and we know what is capital A and capital B. That is what we have found here, and I have just substituted here. And you see, if you further simplify this, I will directly write down the expression anyhow, because I have no time to explain you every step by step. Maybe you will get I of t will be is equal to 0.78125 e power, you will get minus 1.25 t multiplication of j e power 4.3 j t. This value will be minus, and you will get plus j e power minus 4.3 j t. You will get an expression like this. You will get an expression like this, and if you further simplify this, what you will get? So I of t expression can be easily written, right? So I of t, because we know what is this term, right? So you will get minus 1.5625 e power minus 1.25 t, and you will get sine of 4.3 t, right? Now this is the final value of I of t. You try to simplify this one, you will get obviously these two expressions, right? So now this is the A. I will just take it as A, and I will just take it as B. And we know what is V of t and I of t. We try to substitute the t is equal to 1, 2, 3, everything, right? We will see the tabulation now. See, I have just tabulated the voltage and the current separately. I've just substituted t is equal to 0, 0, 0.25, 0.575 and then 1, 1.25, 1.5, 1.75, 2 in this expression and also in this expression. And see what is the results we are getting. At t is equal to 0, then obviously the voltage will be 0 volt. You can easily substitute here. If you put 0, this value will be 1 and this value will be 1. So it will be minus 10. This value becomes 0. So minus 10 plus 10 will be what? It will be 0. And then you go for 0 0.25. I'm getting 3.3. See here at 0 it is 0 and then at 0 0.25 seconds I am getting 3.3 volt and then at 0.5 it is increased to 10.7 around and then at 0.75 seconds it is reaching 14.06 volt. See again at 10 it is reducing to 12.46 and at 1.25 it is going below 10. See what is the ultimate aim, what is going to happen, this 10 volt will be stored in the capacitor. That is the ultimate aim, right? How it is going to be, how it is going to store, that is the thing we are seeing by three ways. One is under damped, one is over damped, sorry, one is critically damped, one is over damped. That is what we have already seen, and today we are seeing the critically damped. And you cannot see anything like this in the critically or over damped condition. You can see from 0 it will be increasing to 10 volt either fastly or comparatively slowly in the over damped condition, critically damped condition. But you never see anything above 10 volt, right? That is the thing we have already seen, right? So now, but you see here at 0.75, it is reaching 14.06 volt, greater than 10. And again at 1, it is reducing to 12.46 and 1.25, it is going below 10. What is the value? It is 9.454 and 1.5 it is going further below to 8.36 and then again at 1.75 it is increasing. It is increasing to 9.11 and at 2 it is again increasing above 10 volt. That is 10.25 and at 2.5 it is going to 10.32 volt. See what is happening. I will just draw the diagram here. Anyhow, see if this is the 10 volt condition, if this is the 10 volt, see it will be increasing and then it is decreasing to below 10 and then again it is increasing above 10 and then it will come to below 10 and it will be doing like this. Maybe this oscillation will reduce after some time and you see here I have just written here after 20 seconds you may put any value of 20 seconds in this t. Instead of t you will obviously get 10 volt, directly 10 volt, exact values of 10, exactly 10 volt you will get. That is the oscillation, that is the damping. If you have LNC 1 over root LC is greater than alpha by R by 2L in the RLC series circuit, then the voltage stored in the capacitor will be oscillating for few cycles, maybe for some time, and then only it will be going to be 10 volts, maybe around flatly 10 volt after some time, like this, like that. The other idea is very simple. What is the current that is going to be stored? Obviously it will be zero. See at the infinity time or at steady state the current in the capacitor will be obviously zero, right? It will be obviously zero and it is going to be zero. And how the current is going to be zero, that is what we are seeing in the three manners. One is critically damped and over damped, that is what we have seen in the previous class. And in the under damped condition, see if this is the zero, if this is the zero, see what happens now. At t is equal to 0, it is 0, there is no issues. T is equal to 0, it will be 0. See at 0.25 it is minus 1 and at 0.5 it is increasing. See if this is minus 1, if this is 0.7 now, see at this time it will be like this and it will be going to 0. Minus 0.7. See at 0.75 what happens? It is 0.05. So positive 0.05 and then it is 0.41. Again it is increasing after some time and it is coming down. Again from 0.441 at 1.25 it is coming down and then at 1.5 it is again going to be 1.5, it is again minus 0.04. At 1.75 it is further decreasing to 0.16, and again you see at 2 minus 2 it is going like this, minus 0.09, maybe less than this, and again 2.5 it is getting to positive. See what happens now, maybe I will draw here. What happens if this is the zero line, then it will be oscillating, bigger oscillation comes first. See if this is 10, bigger oscillations will come first, it will be like this, and it will be slowly dying down to 0, oscillating, and after some time it is going to become 0, right? That is what we are getting from the results. This is what we are telling this condition, particularly this condition, as under damping. What is under damping? The voltage stored in the capacitor will be oscillating for few seconds, and then it is going to be 10 volt, flatly 10 volt. And what happens to the current in the circuit? It will be oscillating over 0, coming down to 0, and then again over 0, and then after some time it becomes flatly 0 amperes. 0 amperes. This is what we are calling it to be under damped condition. See, we have seen all three cases. One is over damped, another one is critically damped, another one is under damped. And we have theoretically explained everything. We have taken an example, 3 scenarios, 3 different R values, and commonly we have taken L and C values, and we have just substituted everything, and we have used pen and paper to get these results. And even though we have solved a problem, we would have not got an exact view of a graph. And in the next class, be very careful or be very interactive in my next lecture, because we are going to take the same example with the MATLAB. In MATLAB, you can easily see 3 different graphs, 3 different scenarios in the same graph. And I am going to tell you how to draw the diagram in the Simulink, and also how to differentiate the graphs. Every basic things I am going to explain you in the next class. Please listen to my next class, that will be very interesting. With pen and paper, even though for our satisfaction we are just going by pen and paper. Anyhow, in the MATLAB you will get a good clarity, and you can easily do so many things using the MATLAB. Anyhow, we are going for the basic things in the next class. Go through this, you will see in the next class. Thank you.